Hi, everyone. Welcome to the P4 workshop. Today's topic is Cross-Federated P4 Research Testbed for Wide Area Programmable Networking Experiments. This is being presented by Mohammad Firas Sada, who is with the UC San Diego Supercomputing Center. He's a researcher there, and he specializes in high-performance computing, deep learning, and advanced networking. He leads initiatives within the National Research Platform, focusing on integrating FPGAs and SmartNICs into scalable AI workflow. Committed to education and research, education and outreach, he mentors interns through programs like Google's Summer of Code. He
Thank
also
you very much.
contributes to workshops and conferences, and he shares insights on network science and programmable networking. Thanks a lot, Mohammed, for joining us.
Thank you very much, Chris, for this introduction, and thank you all for joining this talk and letting me take some of your time to introduce and tell you the story of how we started a P4 research testbed for wide area experiments across multiple environments. This is the story of our P4 testbed on the National Research Platform. And just to give you a brief introduction on what the National Research Platform is, simply put, it's a distributed computing infrastructure that aims to make cyber infrastructure resources available to virtually anybody in both research and education to support and advance both research and education from all disciplines, all science domains. And what that translates to is various heterogeneous hardware resources, including, aside from CPU and memory and compute in general, GPUs, FPGAs, SmartNICs, and naturally that extends to network components like DPUs and plenty of interesting P4 hardware. And of course, this covers use cases from various disciplines in research, from AI, ML, networking, and different science domains, biology, molecular biology, and physics, high energy physics, and so on, and mostly data intensive research. And the way the current shape of NRP is that it's a partnership of more than 80 institutes, and this is increasing very rapidly, led by us as researchers at the University of California, San Diego, and our partners at the University of Nebraska, Lincoln, and the Massachusetts Green High Performance Computing Center. And of course, the aim here is to provide open access to resources. This is especially important in addressing the widening gap between different and the disparities between different institutes, different access in academia to resources, especially in today's world that we live in post Moore's Law, where we're beyond expanding in capacity and expanding in capabilities of the hardware to an area where we're introducing new architectures, new hardware, new kinds of hardware, new use cases, and which complicates adoption in general and complicates setting up the infrastructure for the hardware and the software environments for the hardware and setting up the hardware itself. So we come with a unified Kubernetes cluster that everything falls under called Nautilus that is now spanning across multiple continents to provide one storage pool, one hardware resource pool that provisions all of that hardware with the software environments, the producible experiments, and everything that anyone from research and academia can need to use that hardware. And that's mainly our motivation in establishing a P4 testbed. And as you can see, this is a live dashboard. If you visit the link, you can see it. It's zoomed out. You can see some international resources, but if you zoom in into the United States, you can see we have 100 sites where NRP exists. These are different campuses, different research institutes, different institutions in general, academic institutions. And just a little bit ago, just in January, when we were making a similar slide, the number was 72 sites, and now we're at 100. So you can see NRP is rapidly expanding. And one other resource available on NRP that I'd like to touch base on is Pacific Wave. So Pacific Wave is an internet exchange point connecting the United States and international research and education institutions to advance those large-scale data-intensive workflows and research experiments. And Pacific Wave has added 7 nodes, so 7 Kubernetes nodes, 7 servers that have Bluefield 2 DPUs. And the reason I mentioned the Bluefield 2 DPUs is that they are part of our P4 testbed. And Scenic, who was behind the Pacific Wave, has made those nodes available on Nautilus for virtually anybody in the academic and research community. And another resource I like to talk about is Fabric. So Fabric is a federated testbed and is a funded project that provides international resources as well at 29 sites in the United States and 4 global sites. And Fabric provides plenty of resources, including ConnectX, SmartNICs, FPG, programmable P4 FPGAs, even P4 Tofino switches, and plenty of resources that are available for researchers to provision. And this is one thing we like to talk about because one aspect of our testbed is exploring the interoperability in both NRP and Fabric. As you'll see in a second, they both exist on the same network topologies, on the same network backbones. Another resource is AMPath, which is short for America's Pathway Exchanges, and it's an international research connection point between mainly the United States and Latin America and the Caribbean to basically do as well data flows from Latin America to the United States and vice versa. Ampath has added multiple nodes on NRP as well. Some of them have very interesting hardware like the SN1000 FPGAs or SN1022, which some of you may know them as the rebranded U45 ANS, which are also P4 capable SmartNICs that allow for WAN experiments between multiple continents. And the interesting part here that we're building up to is that all of these resources exist on the same topology. So if you're familiar with the Department of Energy's Energy Sciences Network, or ESNet, it's a network backbone that connects all the national laboratories, all multiple campuses and research institutes, educational institutes across the United States, and plenty of NRP's resources, as you can see on the bottom right corner, and all of Fabric's resources on the bottom left corner exist on NRP's backbone as well as Internet 2's backbone, which you can see on the top right corner. So you can see there's a lot of co-location, there's a lot of overlap, and there's a lot of room for creativity, especially since all of these resources are provisioned for the research community. So they're sitting on the bleeding edge, waiting for experiments where it's not a deployment network. It's okay to break stuff, and that's what we're trying to establish here, pushing the edge, doing interesting P4 research that in a testbed environment where we're allowed to actually provision the hardware, so we're not running simulation, and at the same time we're allowed to break things and experiment uh, different ideas with less constraints, not without constraints, but with lesser constraints. And of course, this is all enabled by using ESNet Sense. So ESNet Sense, simply put, it's an orchestrator software that allows us to provision L2 and L3 paths on ESNet's backbone network on Internet 2. So virtually by using ESNet Sense as a piece of software, we can provision paths between our resources. So if I'm an NRP user, I'm using the Nautilus cluster, I have my pods, my containers. I can use Sense to start L2 paths between two different pods across the WAN, and it will guarantee quality of service. It will have a VLAN interface on this host and a VLAN interface on that host. And those two VLAN, basically MAC VLAN interfaces on the two hosts will be plumbable together through our VLAN network. And that is the aspect that allows us to do our test bed in a WAN fashion. And aside from the Kubernetes overlay, for example, in our cluster, you can see here that the Sense Orchestrator model is end-to-end using API authentication, and we provision that to NRP's users. So we have plenty of users on NRP, thousands of users. We provide them with an in-house built Kubernetes operator, where simply put, I'm not going to dive deep into the details of the operator, but simply put, users can define in their YAML how they want to provision their paths, what node their pod is starting on, what other node the pod is targeting, and the path is bandwidth, and simply adding annotations in their pod's YAML. This allows them to start a VLAN path, L2 path between the two nodes, the two physical hosts, and attach the network interfaces from the hosts to their containers using Kubernetes CNI plugins like Multus and other network attachment definition container network interface plugins. And we try to automate this process as much as possible in our operator, in our pod YAML syntax, so users don't have to deal with multiple layers of abstraction. They just define what they want and it starts for them. And that's the approach that we followed in establishing our P4 testbed and in making it a reproducible testbed. So the testbed itself runs on NRP's hardware, but we don't just stand it up and provision users in. We give the entire infrastructure to the users to provision with the hardware. And a simple example of that is just to give you a brief example of how the interoperable testbed might look like if a user is starting a topology between their three OSs, three systems at WAN. Let's say they're starting a user pod at the San Diego Supercomputer Center on a node on NRP on the National Research Platform. Uh, Using the operator, we enable them to provision a network port with VLAN, a network interface, sorry, with VLAN to that pod, and they can similarly start another one at Ampath in Florida and have the interface peeking into their container. Similarly, on the Fabric testbed, let's say in Starlight in Chicago, they start a VM because so for NRP, the environment is starting user pods, Kubernetes pods. For Fabric, users are starting VMs. Uh, Regardless, despite the heterogeneity, users can still use the interfaces that are plumbed together with the VLAN, and by using CNIs, they can see the interfaces, they can start their own topology, and at that point, using our operator, users can have interoperable network experiments. And this is where the interesting stuff we're building up to comes in, where we can actually implement our P4 experiments. So far we can provision network interfaces. Now comes the part where we talk P4 hardware. And just to simply give you a brief context, so hardware on NRP is very heterogeneous. One example of hardware is GPUs. NRP has various kinds of GPUs from RTX and GTX cards to data center cards that are more optimal for inference for training and more modern architectures like generative AI cards that are not really GPUs but more optimized for inference. And those are resources that users can provision. And at the same time, we have P4 hardware on NRP, and that of course includes Bluefield 2 DPUs. So we have the 7 DPUs we talked about from Pacific Wave at various sites. For example, San Diego, and we have one in Guam and Chicago and so on. And each one of these DPUs has two 100 gigabit per second ports. And of course, they're ConnectX 6 based, but they also have ARM cores, which allows them to use the full capabilities of NVIDIA's Doka, but they're also fully P4 capable. And that's one interesting thing is that NVIDIA recently announced the DPL container and the DPL runtime and running P4 on their Bluefield 3 architecture. And if you visit their documentation, as of the time of making this presentation, you'll see their documentation references Bluefield 3s. But actually in trying to reproduce on Bluefield 2s, we've had success, and we have our Bluefield 2 DPUs running P4 at full throughput of 100 gigabit per second per port on the 7 cards. And since there are resources available on the cluster, this makes them provisionable resource for users to use in their Kubernetes pods. Similarly, one interesting hardware resource we have is the AMD or Xilinx Alveo U55C FPGAs, and I'm calling them SmartNICs in this context because we have 32 of these FPGAs. They're all at the San Diego Supercomputer Center. And these FPGAs also have two 100 gigabit per second ports and 16 gigabytes of high bandwidth memory. The reason I'm calling them SmartNICs is because these cards, these Alveo cards, support the AMD Open NIC shell that allows for P4 programmability. We're using ESNet's own framework that is built as let me call it a flavor of Open NIC shell that allows virtually any user to provision those FPGAs as you can think of them as smart NICs, you can think of them as a small switch on the edge of the network where users virtually have all kinds of command line tools that users normally find in switches for P4 data plane, for control plane data entries, for probe counters, and so on, and for granular control for virtually anything beyond layer 0, so layer 1 and up. And of course, both resources support DPDK, which allows us to do very interesting stuff with them. And another resource is the Tofino 2 switches on NRP as a hardware resource. Of course, the Tofino 2 switches, in our context, their deployment, they're actually running their routed network, they're running the Kubernetes overlay. So their deployment hardware, not really testbed hardware per se. So we're next step for us, the next goal for us is to find a formula of provisioning Tofino 2 switches or switch ports for users in a non-invasive way where users can incorporate Tofino 2s and Tofino 2 P4 in their network topologies from NRP. But it's worth mentioning that the Fabric testbed, on the other hand, does have dedicated Tofino 2 switches that are just for testbed network that are provisionable per user. So one user can actually go on Fabric, request a dedicated Tofino 2 switch or multiple ones, and start their topology and incorporate it as part of their experiment and use the Tofino 2s and the Alveo U280s, for example, on Fabric. There's 28 of them, one on each side. And similar to the U55Cs, each one has two 100 gigabit per second ports and support the exact same software workflow, the ESNet SmartNIC framework and the AMD OpenNIC shell P4. And users can request resources from both Fabric and NRP and do their own interoperable experiments that go beyond the borders of one environment or one ecosystem to the other. And one other resource Fabric Testbed is recently adding is Bluefield 3 DPUs as well, which we mentioned support P4. So all of this is P4 hardware available for the general user community. So is the ASNet SmartNIC framework, which as a software framework, it's all built open source. It's all available on GitHub. It's all completely reproducible for anybody who either has the hardware or has access to the hardware in an environment that's similar to the ones that we're discussing today. And it acts as multiple tools, command line tools, wrappers, Docker compose profiles that make it as easy as plug and play for P4 on Alveo FPGAs. And of course, it provides all the tools that are needed packaged. So users have DPDK preloaded. It's just waiting on a single command and then it's up and running. It has all kinds of packet statistics, probe counters, command line tools, the hooks to connect to the Viro and Virus tools automatically. Users just need to have the software and the licenses, and it does everything end to end, including behavioral simulations over the Xilinx P4 architecture against PCAP files or hex dump files and manual table entries for simulations and as well as hardware simulations and all the pipelines needed for synthesis to go from P4 code and testing against PCAP files to having the artifacts and bit files loaded on the actual hardware to run their P4 workloads. And of course, we provide all of this in our documentation, so it's completely reproducible. Users can go from their P4 knowledge and actually reproduce the examples that we have in provisioning the hardware, loading on FPGAs. There's minimal learning needed. We have the reproducible examples available for everybody. And then in our testbed, we try to make it as reproducible as possible. So our main goal here is not to provide a test bed as much as provide the test bed and provide the ability to, let me call it, to spin up your own test bed. So this is a research environment. We want to give users the most flexibility where they can start their own topologies, start their own experiments, and start whatever. Since we have a plenty of space in access to heterogeneous hardware, we want users to have the ability to start their own P4 test beds across that hardware. And of course, that's all in a scripted fashion where users just use their credentials that they authenticate to the cluster with. And it's all scripted to do everything under the hood for them to provide them with the YAML files that they can interact with Kubernetes with and then start everything that they need. Of course, we provide all the things needed between the software environments, the container images, and the template YAMLs, as well as our running P4 testbed, which we're more than happy to show users how to blend on it itself instead of starting their own and test things on it. And I just want to briefly mention a couple of use cases that we've used the testbed for, and this is why we developed the testbed. So the need for it came from us as researchers and our own personal need for a P4 testbed where we can prototype things, when we can deploy and test in deployment without anything breaking before, let me call it, production. And from our need for that, we're sort of providing it to the rest of the community. And our main use case in it is reaching per packet telemetry, where every single packet on the cluster is stripped from its payload, and every single packet headers are kept and studied in a distributed fashion. And P4, especially on FPGAs, allows us to do so with the nanosecond level timestamping. And this is, of course, following ESNet's own high touch model. They have a similar model where they have used P4 FPGAs, also Alveo cards. Of course, it's closed source, so we're trying to model, but they share the details of their model, so we're trying to model something similar for us as the NRP cluster. Another use case, another experiment that we've done and demonstrated before is replicating the same per packet telemetry, but with just to give it a sort of a demonstration edge, run it with segment routing using SRv6 encapsulation, where we're steering the traffic from the control plane and actually uh, use the control plane to steer traffic between NRP and the Nautilus cluster and the Fabric testbed. This is an example of our experiments where we went from UCSD's Fabric site to UCSD's NRP sites to Fabric's UCSD site, across Starlight in Chicago, to Salt Lake City in Utah, to Washington, and back to the Fabric Siena site, which is it's actually a rack on wheels that is demonstrated on multiple conference exhibition floors throughout the year. So our experiment basically was collecting telemetry data in a modified version of segment routing with SRv6, where we're injecting the timestamp 64-bit header at every single segment for telemetry collection and telemetry analysis. And another example we use the testbed for is prototyping and studying the effects of doing real-time and network machine learning with P4 on FPGAs and on Tofino switches. Of course, that is done by converting fixed point arithmetics to, floating point arithmetic to fixed point, and converting nonlinear functions into Taylor series approximations, and studying the effect of that, and studying the effect of doing inference embedding in network flows, and in adding encapsulated inference workloads, and studying the throughput and latency involved in accomplishing so. And mainly all of our experiments, all of them are open source, and that's the target here. And if you visit docs.nrp.ai, you'll see our documentation. You'll see that every single experiment that we do, including and most importantly the testbed, the main goal here is reproducibility. We aim to reach a level where any user, if they want to, they can spin up their own P4 testbed. They can make use of the fact that they have P4 hardware among many other heterogeneous hardware. So for example, they have P4 hardware next to GPUs, and they can do, for example, study, off the top of my head, P4 research with federated learning, or more interesting stuff, with the access that they get from these free for academics resources, and very heterogeneous resources. And thank you all for listening to me. We've included some links that you might find interesting to learn more about NRP. So NRP's website is nrp.ai, and the Fabric testbed is just whatisfabric.net. You'll see all the information we need about both platforms. And thank you all very much.
Wow, that was really, really impressive. The presentation was great, and it was very well prepared, and the content just blew me away. I could spend hours deep diving into all these things that you pointed us to. My overwhelming sense is that this is very modern. It's like, it seems to follow best practices and patterns from industry that's on the leading edge. It's not like a cloistered academic thing. It seems very relevant and with the times. I like everything you said. I
Thank
could
you.
probably ask 50 questions, but in the interest of time and for our audience, I'll trim it down a bit. And I have a few questions that I just thought of along the way. How long has this been in development? It's quite rich.
Yeah, so it started out from need. It's been in development in general for 2 years now, but it started out from our need as researchers for P4 resources. And
Mhm.
as you can probably already tell from the presentation, our need as researchers was experimenting with P4 on the edge with the FPGAs, the U55Cs. But as we grow to add more hardware and more P4 hardware, and so the Bluefield 2 DPU P4 success, that was last week, to be honest. It wasn't originally part of the presentation. So it's growing as we add more hardware, as we have a wider user community, and as we grow in our use cases for sort of pushing the edge of research with P4.
Yeah, very nice. You have some open source sites that show some example applications. Are those applications something where someone who gets into this network and has access can just, in one sit down get something going? Is it pretty easy to get started for someone so the barrier isn't too high?
So that's what we aim to, and that's what we hope that we have accomplished. We're always, of course, open to feedback and on how easy it is to reproduce, but we have everything designed with reproducibility as the main objective in mind. So we're hoping that whoever sees our documentation, they can reproduce everything.
Yeah, it seems like you're striving for what I've heard as 5 minutes time to first dopamine, meaning you're going to have some feeling of satisfaction very quickly when you get this out of the box. That's great. Um, can the general public have access to any of this, or is it strictly part of a academic or defense, government agency type of realm?
So it's to be honest, it's less government energy agency, more academic community.
Okay.
So
Okay.
virtually anybody from student to PI to staff at research institutes
Mhm.
at universities can access the hardware and can access the examples. Examples, everything we code, everything we do, everything we write, it's completely open source. It's available both on either GitHub or our community GitLab, and it's all open source. But access to the hardware itself is generally for academics. But in the scenario where, let's say, there's industry collaborator working on research with academics, they first get access to the hardware as part of
Oh,
research.
well, that makes sense. Are there university courses built around this?
So this is me speaking more of a personal experience. Back when I was a student, I was a TA for a P4 course at Illinois Tech under Professor Nick Sultana, and w- the material covered in the course was heavily related to this and actually teaching P4 on the FPGAs. We're hoping to mature the testbed so one of the goals we aim to is to have the testbed not just as a prototyping tool, as a research tool, but as a tool to add more P4 in education as well. So have classrooms with P4 more on NRP and Fabric in mind.
It it seems like the test bed itself could be the subject of a research class of a university course. A SDN application. It's fascinating to me. And then the P4 part, takes advantage of it. So here's another question. So some of your applications are probably very performance centric. You want to measure the performance of something, especially if you're bothering to timestamp everything, like I saw in some of your example apps. Do you have a way of characterizing the performance of the network once it's been provisioned, the slice, so to speak, with like independent hardware traffic generators or software traffic generators? So you know what the baseline is before you look at the performance of your application.
Yeah, so this is actually very interesting. So we don't have packet generating hardware beyond traditional switches, FPGAs, and using software tools like PacketGen,
Hmm.
PK, on the cluster. We're always, of course, interested in adding more heterogeneous hardware and experimenting more. But if you can for example, if you're getting your baseline from PacketGen and DPDK and you want to test your hardware, your application per se, you can test against that. Of course, you're dealing with multiple layers, so there are, let me call them real world constraints. So,
Hmm.
for example, two FPGAs on the same host and they're going through the same switch, odds are they are going to get the 100 gig per second that they need.
Yeah.
But let's say you're plumbing through two paths, two hardware resources. Let's say one DPU in Guam, one DPU in at SDSC, for example. And we have SDSC, we have all the FPGAs on one switch. And for the sake of argument, let's say it has 400 gigabit per second uplink. So if we're going more than four ports and assuming there's no other traffic, we're gonna congest it.
Yeah. Yeah.
So there is an aspect where users have to be topology aware of what's happening under the hood to be able to when it comes to measuring and monitoring and putting things in metrics, they have to be topology aware, but that's where we come in. We try to be as hands-on with support as we can.
Have you found that the quality of service, let's say just one point-to-point virtual link from one location to another without worrying about congestion, but just the quality of service of the provision path, one point-to-point connection, is that usually pretty solid? Is it what you
So
asked for?
So in general, because we run on ESNets and Internet 2's backbones, not commodity, but it's amazing. It's very impressive, to be honest. But we have a lot of credit to give to the ESNet Sense Orchestrator because it has very extensive traffic controlling and quality of service features where users, when they're starting the paths, they have different quality of service, let me call them classes. So they can get best effort, which is they specify their bandwidth and they get the best effort that the network can provide realistically. Or they can start a guaranteed capped bandwidth where they are going to get the quality of service, they are going to get the bandwidth, but the path itself is only going to start if the orchestrator can actually communicate with the switch, with the topology, guarantee the bandwidth, and then start the path.
Okay, so it doesn't try to provision things that aren't available, so to speak.
Yeah, exactly. And that's one area we're also exploring in research and actually using and having, let me call it Kubernetes, be provisioning and scheduling network as well as an infrastructure as a resource.
Is any of this adaptable to other, let's say, SDN programmable fabric environments? Let's say a different kind of campus network or distributed network or even a commercial enterprise network. Can people take advantage of this and replicate this test bed?
Yeah. So the cool thing in what we do naturally on both NRP and Fabric is that it's modular and design. So, for example, our testbed relies on a Kubernetes cluster, relies on Multis as a CNI, relies on Sense and VLAN interfaces, relies on, for example, with FPGAs, a specific kind of FPGAs with specific shell. But all of these are modular pieces. So
Mhm.
virtually anybody can adapt and just clone everything, change one piece for the other, and everything should work.
What about the SDN interface where you're actually requesting resources and topologies? Is that abstracted in a way that you could adapt it to some other network operating system?
Uh, in a fashion, yes, it's more tailored towards for us as NRP towards
Hmm.
Kubernetes and for Fabric. Fabric have their own API as well. So in adapting it, there's always going to be some sort of engineering to get it to work naturally. But we hope that it will prove itself to be modular to the point where everyone is comfortable importing if needed.
And I'm thinking that, Sonic is all the rage these days. And I'm thinking that if someone were to take some of this provision and try to apply it to switches that are controlled by Sonic, that might be interesting to someone as an experiment, as a project.
So to be honest, that's what we do under the hood with our NRP switches. They're running Sonic
Oh, okay.
P4 pins. That's what we do. The piece of the puzzle where we're doing it is easy. The piece of the puzzle where we can provision it for the user community is tricky because it's not a dedicated switch. It's switch actually routing the Kubernetes overlay,
Understood.
the
Understood.
uplink to the network.
Well, this was really, really fascinating. It's so cool to see this. What I would say it's pretty hip and modern, being deployed in academia. That's good because people who use this, they're going to get into industry, and it's not like a big jump. This is a real thing. And I think a lot of people might be inspired by this. I am. I wish I had time to play on it. It looks like a lot of fun. So really want to thank you for presenting this to us. And I look forward to seeing how other people respond to this.
Great. Thank you very much for having me. And we have the links on screen. If anybody's interested in the conversation, we're more than happy to dive deeper into the details as well. And thank you all.
Yeah, very nice meeting you.